So thanks for coming. So today we have Martin Ziegler, who's a CS professor at KAIST. He came to KAIST 4 years ago? Or 5 years?
Five and a half years. It's been.
And it's in complexity theory. Complexity theory of continuousness.
Yes.
And today he will talk about quantitative encoding and complexity of continuous data.
Yes, so thank you very much for the opportunity to talk here. Yes, I'm a closeted mathematician. I used to be professor of mathematics for 5 years in Germany. And I really like everything continuous, so kind of complementing the discrete mathematics that you're doing here. And yeah, looking at it from a computational perspective. And what I present here is work with and by my PhD student Im Dong-hyun, who unfortunately he came here, but he was sick, and so he decided he's better going back to bed and recover. But most parts of this are actually his research in his master thesis and his current PhD thesis, and we have been in discussion with Akitoshi Kawamura, who is a long-term collaborator in Japan, first at Tokyo University, then PhD with Stephen Cook, then anyway, now he's in Kyoto. Matthias Schröder from Germany, Svetlana is a research professor here at KAIST, and Florian is another former PhD student of mine. And talk is about quantitative coding and complexity theory of continuous data. Now you all know about complexity theory of discrete data, and you know about coding theory of discrete data. That's mostly like the work of Shannon, for example, or Kolmogorov. But here it's about continuous data. So let me give you a sketch the general picture. Computer science, in the early days we would just start hacking, right? Myself start writing a program, but nowadays computers have become much more bigger in terms of memory, in terms of speed, and also programs have grown in size, and need teams and organization, and for full-fledged software engineering starts with a specification. Then come computability investigations, pioneered by Turing and Kleene, complexity consideration, Joris Hartmanis, Stephen Cook et al. Then semantics of the program, verification of the program, Dana Scott and Tony Hoare, and then starting to really implement and break down the problem into abstract data types, kind of modular software. But this is all well-established technology, right? And the only last step is implementation. But this is all established for discrete data, whereas a majority of actual computational problems deal with continuous data coming from engineering, coming from physics, coming even from mathematics with computer-assisted proofs. For example, dealing with real numbers, dealing with real functions, dealing with operators. And here, the foundation is much less developed. As you see, the arrows kind of ends here in complexity, and issues like semantics and verification of programs operating on real numbers, real functions, operators. There's kind of the workaround is discretize the real numbers using floating point, discretize the function using samples. But this is kind of an artifact, right? All this discretization, this is inherently real continuous data. There's a reason mathematicians proceeded from rational numbers, discrete objects, to real numbers, right? And all kind of undoing all this seems kind of strange. It's like, you know, building tables, not from a tree, but taking the tree, cutting it down into plywood, and then gluing back the plywood. It's kind of, yeah, there are lots of artifacts that come from all this discretization and computing on discretization. And when you prove something about real numbers, you don't resort to the definition of real numbers. You don't start usually arguing about take an equivalence class of Cauchy sequence of fractions. No, that's not how you do it. For reasons, right? What you really exploit are the properties of the real numbers, and information hiding, ignore, forget how they have been constructed. There are many equivalent ways of constructing real numbers. What really matters are the properties. And we should do the same in computation. We should be able to write programs, and most numerical people actually do write programs thinking that they're operating on real numbers, thinking that they're operating on real functions, whereas actually they're operating on discretized versions, and that gives rise to all this trouble and problems coming with numerics. Lots of entire classes, lectures dealing with all these issues that should actually be hidden under the rug. I like to compare it to the sewage in a building. Everybody knows this building has sewage, right? But we prefer not to see it. It should work, but it should be sealed under this very nice floor, and everything should look, kind of like abstraction. Always, we know that computers operate on bits, on bytes, but we should be able, and we abstract from that, we write programs such that they operate on actual mathematical integers without rounding error, overflows and everything. Okay, so that's about real numbers. But when we proceed to more abstract objects, like Sobolev spaces, right? Important concept in the theory of PDEs, or more basically Hilbert space L2. What is the computational complexity theory for Hilbert space? We don't even have a definition. What is a polynomial time computable L2 function, for example? So what we're working on is extending this arrow here from the real setting towards semantics verification. That's what my PhD Sevan is doing. Abstract data types with computable semantics of continuous data. And what I'm talking about here is more general abstract continuous structures, where even the question of complexity is not answered. Fortunately, the question of computability has been answered. The definition of computability has been answered. And what I'm talking about today is basically just this small arrow here. And Doron Zeilberger used to say, in his opinion, that a good lemma is worth 1,000 theorems, and I'd like to add to that. Well, but before the lemma, there's a definition. A good definition is worth 1,000 lemmas, and we don't happen to have the definitions here. That's what I'm talking about today. So, okay. So to start with the motivation, let's start with the discrete setting that you're all aware of. Let's say how to encode a graph. There are various ways of encoding a graph: as adjacency matrix, as a list of edges, or as a rotation map, which is as crucial in low complexity, log space complexity theory. Rotation maps are more common. But the point is, they're all basically equivalent computability theoretically and complexity theoretically, like subject to polynomial time. For integers, there's already two different ways, binary versus unary, and as you know, that makes a huge difference complexity theoretically. Computability, it's the same, we can convert back and forth, but complexity is a huge difference. Encoding a binary number in unary blows it up, and so huge complexity.
So what's the unary? Is it like the number of digits?
Right, yes. Yeah, number of digits. So when you want to, so there's this famous, factoring integers is considered hard, but of course the sieve of Eratosthenes has running time, which is the square root of the integer, right? So that sounds like a polynomial time algorithm, but it's polynomial in the value, that is in the binary length, the number, and not in the binary length. So that's what illustrates this difference. but we have an intuitive understanding which one we should use. Then we should use the binary encoding. And the reason is that the standard model for computation and complexity, the Turing machine, naturally operates on finite binary strings, because here you see a Turing machine, it has this tape, right? And each tape cell can hold a binary digit, 0 or 1, or blank to indicate that here's the end of the string. So that corresponds naturally, binary encoding corresponds naturally to Turing machine computation and complexity theory. But this is right, and when we operate on graphs, we usually operate implicitly on their codes on finite binary strings. But this is all the discrete setting. How about the continuous setting of, let's say, real numbers? Well, the Turing machine model extends naturally and immediately from finite binary strings to infinite binary strings, because the tape is already, by its very definition, infinitely long. So if we just remove the blanks as end indicators, then we immediately have a Turing machine which works on infinite binary strings. Of course, that will take a long time to compute or even read the input, but the model of computation is there already, right? And so the machine model naturally extends from finite binary strings to Counterspace of infinite binary strings. And even more to this higher type space, the space of oracles. So query a finite binary string, answer 0 or 1, that's oracle. So the oracle Turing machine model in Alan Turing's PhD thesis already also gives rise to kind of data type that they can naturally operate on, and other data types we need to encode over these. For all data types of continuum cardinality, right? This has continuum cardinality, this has continuum cardinality. So this is the kind of spaces that we can encode in this way. Here we can encode discrete spaces, and here we can encode spaces of continuum cardinality, and operate on these objects from this space by operating on their codes, because that's what the machine model already does. So this is what I want to talk about, this continuous setting. And already for real numbers, which we think is a really basic object, how would you encode real numbers as infinite binary strings? Make a bet. Make an offer. Binary, exactly. That's a natural thing you can. And actually, that's the thing how actually Alan Turing, in his 1936 paper where he introduced the Turing machine, immediately also defined computing on real numbers using his machines by means of operating on the binary expansion. So here's a formal definition of binary expansion. Right, so here's the sum, the Cn are the coefficients, and 2 to the minus n are the weights, right? And observe that the binary expansion is almost unique. Only the dyadic rationals have 2, precisely 2, and all other numbers have precisely 1 encoding. That will turn out to be relevant later. Here's another way of encoding real numbers. This is arguably, this is what actually Ziegler, like logician, used. Take fractions of natural numbers, of integers, to approximate the real number up to some absolute error. It's a different way of encoding real numbers as a limit of a sequence of certain rational approximations, basically how real numbers are defined as the completion of the rational numbers of the fractions. And here, the encoding is not at all unique, right? You can approximate a real number by various such sequences. Another way of encoding is the dyadic. This is kind of what people in numerics like. So taking a mantissa, like 2 to the n, and that's the exponent, and an being the mantissa, and taking a sequence of longer and longer floating point numbers that approximate the real number with error bound 2 to the minus n. And finally, another way of encoding, which you may be less familiar with, is the signed digit expansion. That's an expansion where we have addition to 0 and +1, also the -1 as a signed digit. And this also gives rise to very non-unique codes, right? So, because here we can kind of, if we add some digit, then we can later, with later digits, subtract something. So there's a lot of non-uniqueness here. And why am I introducing all these encodings? Because the most natural encoding, the binary encoding that you suggested, that Turing considered, is not a suitable way of encoding real numbers, because it makes addition uncomputable. Let me demonstrate that. So I would like you to add these two numbers in binary. And tell me the leading digit. What is the leading digit of the result? And you're a Turing machine, okay? So, right? So,
I was going to say 1, but then you told me that's a Turing machine.
So you're saying 1?
Right.
Right.
There's another unique encoding.
Yeah, that's true. It's not unique. So your guess is 1. Fair enough. But actually, what you don't know is that the numbers continue like this. Okay, now I've fooled you, right? But I've not really fooled you. I fooled a Turing machine, because a Turing machine cannot know the entire string in finite time, right? It starts reading here, and at some point in finite time, it must decide what digit will it output here, right? And so it cannot know this. And the same, of course, works if someone else were to guess that the leading digit is 0, then I'm just going to fool it in that way, right? So in either way, the problem, if you look at it, it's because they are unboundedly long-ranging carries, right? Sequence of carries, but computation must output this digit after having made a finite number of steps, arbitrarily large but finite, and beyond that, it doesn't even know the input. So that's what actually led Alan Turing to publish, a few months after his paper, a correction. There are 2 papers by Turing. The first is Turing machine, and the second is a correction where he changed his definition and proceeded to this definition. Okay? So the message here is, it's very easy already with real numbers to arrive at a unsuitable notion of encoding, which is very different from the discrete setting, where it's whatever you reasonably come up with is usually a good setting. So what about the next one? Is that a good way of encoding? Well, it turns out that this is a good encoding in the sense that it makes the arithmetic operations computable, and all the usual functions that you know, exponential functions, so analytic functions, transcendental things, everything becomes computable. So this is a good encoding for computability investigations. So there's also theorems that say certain real numbers are not computable, which is, can you see easily from cardinality consideration, because there are uncountably many real numbers, but only countably many algorithms, countably many Turing machines, and you can encode the halting problem in such a real number. But the baseline is for computability. This is a good setting. However, for complexity, computational complexity, this is again an unsuitable setting, because, well, for example, excision is computable, but it is not computable in bounded time, which is kind of strange, right? You would think adding to the real numbers should be something simple, but here it cannot be done in bounded time. And again, let me demonstrate you why that it's for very simple reason. Maybe let's encode the input. So let's encode the input 1 over 3, or I'm going to be, let's encode this by the following sequence of fractions. So 1 over 2, it's a good approximation, 2 over 4, 4 over 8, and so on, right? Or 2 to the k divided by 2 to the k plus 1. So what you see here, these are all very good approximations, actually without error, but they're very long. This one is k bits long. So to even read this approximation, a Turing machine will need unboundedly long time. Okay? So giving unnecessarily good, okay, so you could say you can cancel this, but you can do the same with a small perturbation to prohibit canceling. The point is, since there's no bound on these numbers, numerator and denominator separately, they can be arbitrarily long and take arbitrarily long for a machine to even read before again it can start producing any sensible output. So technically this means because this encoding is not proper, its domain is not compact. So computability, theoretically it's good, complexity theoretically makes no sense. This, on the other hand, is good for both computability and complexity up to polynomial time. Because, well, how long is, let's say we consider addition, let's say from the unit interval to the unit interval, well, almost the unit interval. How long can the nth numerator be? Well, since the input is a real number between 0 and 1, the largest numerator here is 2 to the n, or 2 to the n plus 1. Otherwise, this here, because of this error bound, right? So that means in order to access the error 2 to the minus n approximation, we only need to, on the Turing tape, there's this A0, worst approximation, A1, A2, and so on, and somewhere here is AN, and the binary length of AN is roughly n bits. That's an important thing. There's a bound on how long this is. So for a Turing machine to access that, these are all binary encoded integers, it must skip over at most n squared asymptotically bits, right? So all these lengths are did. So that's the difference from this encoding, where there are arbitrarily long number of bits to be read, and here it's only n squared bits. So what would you expect that to take? You would expect it to take time order of n, linear time, right? But it takes quadratic time, which is good enough when we're interested in polynomial time complexity, but not good enough when we're interested in smaller complexity like n log n, right? For n log n complexity, there's no algorithm that can do running time n log n in this encoding, because it already needs n squared steps to even get to the approximation of order n, right? So from the polynomial time perspective, this is a good encoding, but from the linear or subquadratic perspective, it's not. Whereas this one, the most unusual one probably from your perspective, this is actually the best one, because here addition can show that it is computable in linear time, actually by an automaton. So I'm not going to show you the proof or the construction, but the baseline is when you're interested in computational complexity smaller than n squared, this is your encoding. So the message to take from this slide is, already for real numbers, there are various encodings, but the most intuitive ones is unsuitable even for computability. Others are suitable for computability, but not for complexity. Others are good for polynomial time complexity, but not for finer picture. And for finer picture, this is your encoding. And now, this is all well known for the real case. But how about now if you look at a more general space? As I said, some abstract space, Hilbert space L2, Sobolev space. To even study computational complexity of PDEs, we don't even have the definition because we don't know how to encode it. Popular ways of encoding L2 functions are, for example, with Fourier series or with this piecewise constant function, the basic function, you know, the completion of the piecewise constant functions in the L2 norm, that gives rise to the L2 space. Two equivalent ways of constructing it. They are computably equivalent, but complexity theoretically there's a huge difference, an exponential difference, and we don't know which encoding to use. So how can we get some guidance on criteria on what encodings we should use, what encodings we can expect when we're given a space? And this is the question that I've been pursuing with my second PhD student now, Donathan Lim. Florian Steinberg already wrote a PhD thesis, and still we are not have not found conclusive criteria. So what we want is criterion saying that given this space, you should use this encoding, and this encoding has these and these complexity theoretical properties, and such an encoding exists. That's the kind of research we're doing, and as I said, the important thing is to find definitions and theorems that say the definitions are reasonable and non-empty. Yes, sure.
The last time, what happened with your example? 0, 1, 0, 1, 1, 0, 1, 0, and that together. Seems like we still have.
Very good question. Yes. Thank you. Let's do that. Let's see here. So here we're going to start writing. Let's see, we're going to write 1 here and 0, 0, 0. Okay. And now when the surprise hits, then we put a -1 here. You see what I mean? Yes? So the thing is, with the binary expansion, we can only kind of correct our approximation upwards, right? But we can never correct it downwards. With this one, we can symmetrically correct and improve our approximation in both ways. That's a good question. Is that a good answer? Yes. Okay. So yes, half of my time is already over, but anyway. So we've already talked about encoding real numbers, binary, rational, dyadic, and signed. What I want to talk about is criteria for encoding generic spaces, metric spaces, compact metric spaces, and an important criterion will be, or important approaches to take the existing computability theory, that's computable analysis, theory of how to define computability and how to encode topological spaces, qualitative theory, computability is a qualitative property after all, and how to refine that quantitatively, namely in the category of metric spaces. And an important step here is to refine qualitative continuity, right? The function is either continuous or it's not. Quantitatively, to say this function is more continuous than this function, and the method to do that is by using a modulus of continuity. Some may remember that from your early days of calculus, modulus of continuity. Okay, then I'm going to recall with the basic spaces and the properties that Turing machines and Oracle machines can already naturally operate on, and what quantitative properties follows from this computation. So, for example, with an infinite binary string as input for a machine to access the nth bit, obviously it must make at least n steps in order to even get there. So any output that the machine creates after n steps can only depend on the first n bits of input. And that's a continuity property, namely a statement about continuity in the Counterspace. Counterspace of infinite binary sequence when equipped with this, the Counterspace metric, right? Counterspace metric is the distance between two such infinite binary strings is 2 to the minus the minimum least n where the two differ. Okay. So, and intuitively, in order to actually identify and see that the two infinite strings are different, provided they are, it takes a Turing machine at least n steps to realize that. And any computation, any output it makes based on this computation can depend only on the first n bits when the machine makes n steps. So that gives rise to connection between computational cost and quantitative continuity on basic spaces. And then we talk about coding other abstract spaces over such basic spaces and operating on such objects by means of transforming codes. And the computational complexity and the qualitative and quantitative topological and metric properties that this induces from the encodings. The technical term is a representation. This is not a representation that you know from algebra. This is a different kind of representation. And the criterion that has been identified 35 years ago, 1985, is an admissible representation. I will define what an admissible representation is. These are the representations, these are the codes that are computability theoretically good and reasonable. Like the binary encoding is not, but these other three encodings are good computability theoretically. That's well-established theory, which I will recall, because that will provide us with guidance to turn that into a quantitative theory. So the admissibility criterion is crucial for the so-called main theorem of computable analysis, which I'm going to recall. And our research is about turning this qualitative definition and the qualitative theorem into a quantitative definition and a quantitative theorem. So our goal is to define admissibility, a quantitative version of admissibility, such that the qualitative main theorem, which I recall, translates into a quantitative one for the category of metric spaces, whereas this theory, computability theory, is for the category of topological spaces. Okay. Right. So let me remind you of quantitative continuity. So let's fix two metric spaces, and modulus of continuity of some function is an integer mapping such that says whenever the two arguments are that close as kind of imagine the first mu of n bits coincide, imagine roughly, then the function values coincide up to the first n bits. Okay, so that says mu says how much information about the argument we need to know information theoretically in order to get approximations to the value. And I will give some examples in a minute, but the first natural property is know that the composition of two continuous function is again continuous, right? And the quantitative version says if the first function has modulus mu and the second function has modulus nu, then the composition has modulus mu composed with mu. And observe that the order gets reversed because this conception of a modulus says how much input we need to get the output. You may recall from calculus a different notion of modulus as a function, as a non-decreasing function from real numbers to real numbers. That's not what we consider here. This is kind of like bit information theoretically. That's why everything is raised to the power of 2. So, and now we can rephrase some classical notions of quantitative continuity in this new setting. For example, Lipschitz continuity that you know. Lipschitz continuity means that the modulus is n, identity, plus some constant. It's the same thing as Lipschitz continuity. Hölder continuity is the same as having a linear modulus. So, yeah, intuitively, basically, yeah, the exponent becomes here the factor, and the constant factor becomes the offset because it's all raised to the power of 2. So we capture classical notions of quantitative continuity in this setting, but we also have functions that are continuous, uniformly continuous, right? Which have no linear, not even a polynomial modulus of continuity. Here is such an example of a function which is so extremely steep here that it does not have a modulus of continuity, or put differently, more intuitively. In order to approximate that function here, up to error 2 to the minus n, we need to know the argument up to error 2 to the minus 2 to the n. Much, because it's so extremely steep. Okay? And we can iterate that. So compose the function with itself. So it maps the unit interval to the unit interval. Has a doubly exponential modulus, but no singly exponential modulus. So we can do kind of all the usual complexity theory, like Prigogine hierarchy with powers and everything, but now in this metric setting of quantitative continuity. Okay. This makes sense, right? By the way, please interrupt me if you have questions. I'd rather discuss than lose you. Okay, good. Right. So that's one aspect, quantitative continuity. The other aspect is the kind of spaces that Turing machines naturally operate on. So classical Turing machines operate on finite binary strings. Everything else is encoded over finite binary strings. The extension of the two infinite binary sequences is sometimes called a type 2 machine. That basically means it operates on Counterspace, right? And the Oracle Turing machine model is something that operates on, so this is mixed type, finite binary strings, and here these are kind of the Oracle queries, and the answer says yes or no to the Oracle query, and the output is 0 or 1. So we can kind of curry that as a mapping from here to here. Let me show that again. So currying that to this side gives rise to this mapping. So that's the kind of spaces where we don't need codes for, because they're already the machine can operate on, and we have some properties. Well, and we can imagine, nobody has defined, but we can now imagine climbing up that hierarchy, right? And like to call it this a hyper machine, climbing up a hierarchy of higher and higher order spaces. And different aspect of our research is to devise a computational complexity theory for such hyper machines, but I'm not going to talk about that here. This is the metric on Counterspace or Oracle space that I already introduced, and it has 3 main properties of computing on these basic spaces, which we'll use as guidance to devise criteria and notions of computational complexity on other spaces and their codes. First property is that whenever computation operates on a compact subset of any of these spaces of Counterspace, let's just say, then it works in bounded time. So now I have not told you what it means to compute in time t of n, because as you recall, both input and output are infinite, right? So the machine will never actually terminate. So what we mean with to compute in time t of n means how many steps it takes until the nth output occurs. So that's a different kind of notion of computational cost than the one you are used to. You're used to measure the computational cost independence on the binary input length. And you don't care about what is the output length. Here, since the input is infinite, that definition makes no sense. Instead, we measure how many steps it takes until the nth output occurs. Okay? And if the nth output occurs after n squared steps, then we say this is a quadratic computation. If it occurs after 2n to the n steps, then we say this is exponential time computation. And an important property is that there's a worst case computational cost. In the discrete setting, this is obvious, right? In the discrete setting, where we measure computational cost independence on the input length, how many inputs of length n are there? At most 2 to the n. If the computation is total, if it terminates on any of these 2 to the n strings, then we can just take the maximum, and that's our worst case bound. But here, when the input consists of binary sequences, infinite binary sequences, a subset of Counterspace, which is uncountable, then even if the computational terminates, outputs the nth symbol after some finite time, we cannot just take the maximum of all this computation because they're uncountable. I mean, why would their maximum exist, right? But interesting thing is, if the subset of Counterspace is compact, then we can use the continuity argument to show that this indeed has a time bound. So compactness is a crucial property, and if you think about it, that's already true in the discrete setting, but you never saw it, because in the discrete setting, the set is compact if and only if it's finite, and there you can take the maximum running time as a worst case, right? Here, this is a generalization of being finite, being compact. First property. Second property, any function that is computable by such a machine model from and to one of these basic spaces must necessarily be continuous. That's the thing I just said here, basically, right? In order to output the nth digit in time t of n, the input could only be read up to the t of nth position. Okay, so let's say that. So consider transformation from Counterspace to Counterspace. So the machine starts outputting digits, the nth digit, while keeping reading, but it cannot first read the input and then start outputting. It will never get to output something if it first tries to read the entire input, because that's infinite, right? So it must kind of interleave or alternate, read, write, and if it outputs something in the nth digit, and it took t of n steps, then until that time, the machine was only able to read up to the t of nth part of the input. That part of the input cannot affect the output, and that's the definition of continuity in the Counterspace metric. And that's our third property. If a function on Counterspaces or any of these basics is computable in time t of n, then actually it has a modulus t of n. So connection between computational cost and quantitative continuity, as we've discussed on the previous slide. So we already see many new effects in this setting of operating on infinite sequences, on infinite data. And now what can we do? How can we define encodings? So let's first define some complexity. Oh, I'm running out of time, but okay. Let's first define what means to compute something in polynomial time. It means that the nth symbol should appear in time mu of polynomial of n. So that's an important concept. So when you consider classical computation, discrete computation, there's this notion that you measure the cost in dependence on the binary input length. But there's also something called output sensitive complexity, where you measure it in dependence on the length of the output. Because if the output is very long, then there's no way to output that in a short time. So it's kind of not the machine's fault if it takes long to output something long. So, and this is kind of a similar version. So if a function has a large modulus of continuity, then by this property, it cannot be computed in short time, right? So we define polynomial time computability to be relative to the modulus of continuity, thus granting the machine more time to compute if the function under consideration has a large modulus. Okay. So now we've talked about computing on basic function and basic function spaces, Counterspace, right? And this is the higher order space, but in view of the time, let me skip over that and instead talk now about how to encode things over, let's say, Counterspace. So this is a qualitative theory of Kreitz and Weber from 1985, defining what it means to encode something. A representation is a surjective partial mapping from Counterspace. So this symbol here means partial, and it must be surjective. And the intuition is that those infinite binary strings that get mapped to some small x are the names of this x. Okay? And we want to make sure that every element in this abstract space has at least one name. So we require it to be surjective, but not necessarily injective, as we've already seen in the real case, right? All the encodings in the real case are far from being injective. And now what does it mean to transform to compute a function between such spaces equipped with encodings? Here's the picture that I'd like to show. So here we have two basic spaces. Here we have one way of encoding the space x over this basic space, call this encoding psi. Here we have another way of encoding a space y over basic space using epsilon, and a function between these spaces. To compute such a function means to transform names. So every name of an element here should be translated to a name here, which basically means that this diagram must commute. And this is the definition that you see here. And this here, this transformation on the codes is called the realizer with respect to these codes of this function. And now remember, any such transformation on this abstract space must be continuous. And the important criterion says, which we'll see in a minute, the function f is continuous if and only if it has a continuous such translation. So for good encodes, the topological qualitative property of this function corresponds uniquely to same properties of the translation on codes. And for bad codes, this is not the case like for the binary code. So since I am running out of time, let me briefly think how to shortcut. Yes. Okay, yes. So yeah, don't worry, I'm not going over time, but I need to perform some surgery on the slides. So these are the 4 encodings of real numbers that we previously introduced, and now we can review them from this abstract perspective of this qualitative coding theory. And the important property is that any computable function on real numbers is continuous, and conversely, any function that is continuous has a continuous translator between names here and here and here, but not with respect to the binary encoding. And the criterion that captures that abstractly is, as I said, admissibility. Encoding is called admissible if it first is continuous. So what does that mean? Recall that the code, the mapping maps from Counterspace here, which has a topology, onto, where are we? No, one more back. Right. From Counterspace, which with its topology, onto the space we want to encode, which also has a topology, and so we can define what it means to be continuous. And the first criterion is this mapping must be continuous, and the second condition is it must be maximal among all such continuous mappings with respect to a notion of reduction, which I'll define in a minute. But let me emphasize that it's very similar to, for example, to NP completeness. What does it mean to be NP complete? First, it must be in NP. That's the corresponding to here. And it must be maximal among all NP problems with respect to polynomial time reduction, which is basically just a partial order. And the same categorical concept is underlying here. So it basically means it must be a maximum object, right? Maximum. Not maximal, but maximum. And right now I need to tell you what it means, this new notion of continuous reduction. It means to be able to translate codes continuously. This is the definition, but since I'm running out of time and I haven't even started to talk about complexity, let me skip to the take-home message. Okay. Take-home message is here. Okay. Yes. So the take-home message is a dictionary for translating between the existing qualitative notions that have been developed since Turing's work, qualitative notions like computable, topology, continuity, compact, continuous image of a compact set is compact, and equilogical spaces as considered, for example, by Bauer, Birkedal, and Dana Scott. And that our dictionary translates these quantitative notions, where the first entries in the dictionary are kind of obvious. Computability translates to complexity, qualitative computability, quantitative complexity. Qualitative topology translates to quantitative metric properties. Uniform continuity, qualitative, translates to quantitatively modulus of continuity, as I introduced with this Lipschitz and Hölder and so on. Compactness as a qualitative property translates to entropy, which is the part I didn't really have time to get into. Kolmogorov entropy is a quantitative version of compactness. The continuous image of a compact set is compact again. And my PhD student Florian had in his PhD thesis devised a quantitative version for that says if the function has a certain modulus of continuity and if the domain has a certain entropy, quantitative version of compactness, then the image is not just compact but also has a certain entropy. And finally, the spaces over which to use as encodings, Counterspace or this orbital space, or many other spaces like these equilogical spaces for computability consideration. The right category for complexity considerations are compact ultrametric spaces. And as you see, Counterspace and Erdős-Space and are indeed all compact ultrametric spaces. And what we've devised are qualitative. So we took the qualitative notions from the existing coding and computability theory, and we have refined them very carefully into quantitative notions, polynomial version of admissibility, polynomial continuous reduction, polynomial main theorem that translates continuity of the function to continuity of the translator on codes. And what we're working on is kind of defining that from polynomial to linear. That turns out to be, well, the definitions are obvious, but we cannot prove sufficiently many spaces to have such an encoding, right? So far currently there's a danger that this part of our theory is a theorem about the empty set. So the signed digit representation encoding is this, but we haven't found any other yet. And we're looking for spaces to try to prove that sufficiently many spaces admit such a code. Okay, so yeah, time is up. I have plenty of more to say. Actually, I've given an entire semester course, which is available on YouTube. So if you're really keen, you can listen to like 35 hours of lecture on the lecture is called Algorithmic Foundations of Numerics, Computer Science of Continuous Data in our lab's YouTube channel. So that's all for now and for today. Thanks for your attention. And if you have further questions, be careful to ask them.
Thank you. Question? I was confused about. So this Steinberg's lemma is your contribution with the Donghyun, or is it?
No, that's Steinberg was my I think third PhD student, and in his thesis. It's a very simple lemma. If you see the statement, you immediately get the proof. But the interesting thing is that this exhibits an important constraint on how good actually an encoding can be, because encodings map, as you recall, from Counterspace onto the space under consideration. Now, Counterspace has linear entropy. I didn't have the time to recall for you Kolmogorov's notion of entropy. But if this space has a large entropy, then there's no such encoding with small modulus with good quantitative continuity. So that exhibits strong information theoretic constraints, and that gives rise to our definition on polynomial admissibility. So quantitative admissibility requires that the encoding be continuous, which is a qualitative property, and our definition of polynomial admissibility says that it must be quantitatively continuous as close as possible to the information theoretic constraint that is expressed in this lemma. So that's the rough picture. Yeah, so maybe if you really want, I should show the actual theorem. It seems reasonable. Right. Don't skip ahead too much. So here's the theorem. Right. So here's the definition of what it means for encoding to be polynomially admissible. It must have modulus quantitative continuity, which is up to a polynomial as close as possible to the entropy as Florian Steinberg's lemma permits, and it must be maximal with respect to this polynomial version of continuous reduction, not computable polynomial time, but polynomial modulus. So it's an information theoretic, and the theorem says first, or main theorem says that this notion of reduction is indeed transitive. It took a lot of effort to arrive at such a notion, but at such a partial order, but of course it must be transitive to be reasonable. Next statement says this is not a theorem about the empty set. Every compact space with certain reasonable entropy has such a encoding, and whenever we have such an encoding, there's a quantitative relation, not just a qualitative. That was the previous theory. Qualitative continuity corresponds to quantitative continuity of the translation. That's an existing theory, and our strengthening says whenever we have a modulus of continuity here, that leads to a modulus of continuity here, and vice versa. When we have a modulus of continuity, the quantitative continuity promise here, then that gives rise to a quantitative continuity property here. That's our main theory.
So we have a question from the chat. What is the main motivation of the main theorem on this to relate the two different notions, computability and continuity?
Right, thank you. Good question. So, in the computability theory, this relation gives rise to this criterion on what constitutes a good and what constitutes a bad encoding for computability purposes. So the binary encoding is bad for computability, which you can see from the example, but if you have an abstract space, how do you know which encoding is good and which one is bad? And the answer is the ones that translate between continuity from here and here. And now asking the same question for complexity, that's our new contribution. In the real case, by looking at the specific encodings, we can say this is bad, complexity theoretically, this is polynomially good, and this is even linearly good. And now doing the same for an abstract space, that's our research. Using as guidance the quantitative versions of continuity should translate to quantitative continuity here and back.
So when you were looking at the real, just this example with the encodings of the real numbers, you're also looking at addition, and the claim is that, for example, in the third encoding, you have to look at the first n squared bits of the input in order to output the nth bit when you're adding these two numbers. But if you have some other function that you're, so is the encoding connected both to this interval 0, 1 and the function of addition?
Right. So addition is a continuous function, right? So
and it has a particular modulus of continuity.
It is Lipschitz continuous, right?
Yeah.
So that means a good code should be one that makes the transformation on codes also continuous and even polynomially continuous, or even better, also Lipschitz continuous. That's a good code. The binary code violates that. The binary code translates continuous addition to a discontinuous transformation on codes.
This is just addition here was just an example.
Exactly.
Here's a continuous.
Right. Yes. Good question. Yes. Addition was an example of
For any continuous function, in fact, is alternating with, I don't know, what the signed representation would give you.
Right. So Yes, for the sign representation, whenever this function has a linear modulus, then also the translation of code has a linear modulus. And for this dyadic encoding, if this function has a polynomial modulus, then the translation of codes has a polynomial modulus and vice versa. So that's abstract.
Do you get any advantage by using a signed representation if you only have a polynomial bound on the modulus of underlying function?
No. When you're looking for the polynomial perspective, there's no benefit from using the signed encoding, but when you're looking at them more closely, quantitatively, then there's the benefit. Okay, good.
Any other questions? So if not, let's thank the speaker. Hey.